Welcome to the Computer Science program at the King Abdullah University of Science and Technology. My name is Peter Wonka, and I am the chair of the program. KAUST is a research university that hosts students and faculty from all over the world at a modern campus on the coast of the Red Sea in Saudi Arabia. KAUST provides state-of-the-art research facilities together with guaranteed funding and offers master's and Ph.D. degrees exclusively. In the computer science program, we focus on all aspects of knowledge extraction from big data to achieve economic prosperity and improve the quality of life. We conduct research and teaching in the entire spectrum of large-scale simulations, smart networks, parallel and distributed systems, data science, visualization, machine learning, and artificial intelligence. Our graduates are prepared for internationally competitive careers in the industry or academia and leadership in the knowledge-based economy. In the Computational Biosciences Research Center, computer scientists work together with biologists. They use machine learning and artificial intelligence to analyze DNA sequences to find new treatments for diabetes or produce biofuels from microbes. In the Visual Computing Center, researchers run deep learning algorithms on large GPU clusters to automatically recognize actions in videos. They also use immersive three-dimensional cave facilities to visualize the human brain in stunning details. The Extreme Computing Center is home of Shaheen, one of the fastest supercomputers in the world. Researchers develop algorithms that scale to hundreds of thousands of CPU cores to simulate complex phenomena such as climate, clean combustion, and seismic waves. The high quality of research and education is reflected in the placements of our alumni. Some of our former students continue their academic careers in top universities such as Carnegie Mellon University, Imperial College, and University of Waterloo, or research centers including the London Institute of Cancer Research and IBM Watson. Others choose stimulating, high-paying jobs in the industry, either internationally in companies like Amazon, Microsoft, and Yahoo, or inside Saudi Arabia, such as in Aramco, the world's largest oil producer. Some of our alumni start their own companies with the help of our incubation center. FalconVis, for instance, is a successful startup specializing in unmanned aerial vehicles. We are looking for well-qualified people from all over the world at all levels of expertise. There are numerous opportunities for internships, masters, and Ph.D. studies, postdocs, research collaborations, and faculty positions. I invite you to explore our website. I will be glad to answer any questions, and I look forward to meeting you at KAUST.
The Computer Science program at KAUST offers fully funded graduate, master's, or Ph.D. in different areas of expertise. We are a specialized department with exceptional facilities. Our students and partners have access to a supercomputer, which is located on the campus, and we have visualization and imaging facilities. Our faculty are publishing in high-profile journals, and there are some really exciting projects happening across the board, from smart devices to autonomous vehicles. KAUST is a wonderful place to test many new theories and technologies. Our specializations include high-performance computing, cybersecurity and resilient computing, computational bioscience, visual computing and image processing, machine learning and artificial intelligence, computer networks and cloud computing, big data, systems, and databases. Every admitted student in SIMSI receives the KAUST Fellowship, and it is free to submit an application. Our graduates are very successful, and many of them go on to work in high-profile industry positions or other excellent research institutions. The university is a modern town and campus, and all of the labs and facilities are within walking distance. We have around 30 faculty in the computer science program, many of them hosting interns and graduate students, helping to prepare the next generation of researchers within important areas of computer science. We can help you or your students to find the correct research group depending on previous experience and interests.
Hello, my name is Peter Wonka, and I will present an overview of the Visual Computing Center at KAUST, also called VCC. The VCC currently has 9 faculty members who publish academic research in the areas of computer vision, computer graphics, visualization, and machine learning. Altogether, the VCC has about 150 people, including faculty, research scientists, postdocs, students, interns, and staff. The VCC is well embedded in the international research community, and our researchers collaborate with other great universities, industrial partners, and the government. We strive for academic excellence, as evidenced by high rankings from websites, such as CS Rankings, that track publications in the best conferences in different subject areas. After leaving the VCC, our alumni find employment in other prestigious universities as faculty or postdocs, or in leading companies or startups in the field. The VCC is organized according to the Visual Computing Pipeline. The center has research groups whose experience together cover all stages of the pipeline. I will now quickly walk you through the pipeline to give you an impression of the research we are doing in the center. In the computational imaging stage, we consider various forms of data, such as single images, videos, laser scans, industrial tomography, or cryo-EM. After acquisition, visual data is being processed to complete tasks such as object recognition, segmentation, action recognition, and 3D reconstruction. New designs can be generated based on acquired data or even starting from scratch. Example projects in our center deal with architectural designs, CNC machining, modeling of molecular structures, or editing of photographs and videos. Simulation is used to breathe life into geometric data in complex designs, and to evaluate them within different environments. For example, we can analyze the implications of climate change on different urban design proposals and specify strategies to mitigate the impact of natural disasters. Visualization is used to present large-scale datasets from previous stages, such as weather simulation data, molecular structures, brain scans, or geological data from the oil industry. Based on the experience gained in applied projects, our faculty also contribute to theoretical foundations in geometry, optimization, numerical simulation, and machine learning. These theoretical foundations are useful to inform the next generation of algorithm development. Next, we will show selected research highlights.
Oke, Assalamualaikum warahmatullahi wabarakatuh. Selamat malam ya, waktu Indonesia bagian Barat. Bapak Ibu bisa mendengar suara saya dengan jelas? Halo? Halo, Bapak Ibu, kita cek sound dulu.
Iya Mas,
Kita akan mulai.
kedengeran.
Jelas Pak.
Terima kasih. Siap, terima kasih. International Webinar, KAUST Research and Technology, or King Abdullah University of Science and Technology 2023. Those are the information for today webinar. The session will begin shortly. Thank you. Syukran lakum. Syekh. Well, ladies and gentlemen, may I have your attention, please? Our session is about to begin. Please have a nice seat. Thank you. Good night, ladies and gentlemen, for Indonesia time, or waktu Indonesia bagian Barat, and also good afternoon if you are now in Kingdom Saudi Arabia. Assalamualaikum warahmatullahi wabarakatuh. Welcome to the international webinar, KAUST, or King Abdullah University of Science and Technology 2023. I am Ripto Mukti from BelajarBerbagiID, your host for today. I also would like to greet and thank you to our speaker today, Mr. Kai from Ph.D. researcher, King Abdullah University of Science and Technology, Kingdom of Saudi Arabia. Ladies and gentlemen, please allow me for first to read the agenda for today. The first agenda is the opening session, dua and group of photo. I will lead the dua directly. So we will start from dua. Jadi Bapak Ibu, kita akan berdoa dulu sesuai dengan kepercayaan masing-masing. So dua prayer start from now. Finish or selesai. Jesu. Ladies and gentlemen, Tajahau, please allow me first to read the agenda for today. Okay, we will start for the group of photo after the dua prayer. Please, participant can open your camera on the computer. Please open. Thank you for open your camera. We will start from 3, 3, 2, and 1. Okay. So we start 3. Okay. Please smile, or you can also give the love language like sarang heo or love. Okay, everything is okay. Thank you so much, Brother Kai, to join this for coming. Selamat. Thank you. Okay, we will start for 3. Bapak Ibu bisa open kamera ya. Siap. Kita mulai lagi ya. 3, 3, 2, and again 2. Okay. 2, 1.5 atau 1,5. Boleh ya, boleh senyum ya. Kita lagi detect nih ya Bapak Ibu. So we try to detect your smile. Maybe your smile will be upload in our social media. Your smile. Thank you. 1.5. Okay, 1 again, and the last one. Okay. And finish. Thank you. Masya Allah. Terima kasih Bapak Ibu. Thank you so much for participant to open your camera. Ladies and gentlemen, we are finished in the opening session. Without the further ado, I would like to invite Mr. Kai. Previously, we will read out the curriculum vitae or brief of bio Mr. Kai. Mr. Kai, he is a Ph.D. student under the supervision of Professor Peter Terik. So if you see the video, you can see the Professor Peter Terik in the opening of video from the computer science KAUST. Before that, he received master degree from KAUST in December 2021. And also Bachelor of Engineering with honor from Xi'an Jiaotong University or Xi'an Jiaotong Taishui, China in June 2019. He has experience about our internship at the Tencent AI Lab, CMU, Q Lab, and US, and also the Sense Time. And also Mr. Kai has research interest about the machine learning optimization in the large-scale data or model era, and also about the conceptual level knowledge transfer learning, theory, and application. Specifically, he worked on machine learning optimization, federated learning, and a bit zero-shot learning. So please welcome our speaker today, Mr. Kai. Good afternoon, Brother Kai. 谢谢来在我的 webinar， 很辛苦你。Hello, Brother Kai, Mr. Kai. Can you hear my voice?
Yes, thank you so much for the introduction.
How are you today?
Yeah, I'm fine, yes.
Thank you. Really, we are appreciate you are coming in our beginner today in BelajarBerbagiID. BelajarBerbagiID is the social education platform to facilitate participant or Indonesian to reach their dream like the scholarship and also research in abroad or overseas. Thank you again. Thank you so much for coming. So time is yours. You can starting for your presentation.
Okay. So can you see my screen?
Yes, we can see your screen.
Okay, let me get started. So today I would like to discuss my recent research with you all. The main topic is accelerated local training methods in federated learning. So before going deeper, let me give you a brief motivation and introduction of what exactly is federated learning. So in nowadays, we all know that data is collected at the local clients, as we are showing here that the mobile phone, laptop, or even the smart watches can contain all the data, but they are collected at the local clients instead of the centralized setting. However, collecting and training data in the centralized fashion in this scenario is impractical because we have the communication cost limits and the memory constraint limits as well. And most importantly, nowadays, the privacy is also a very crucial factor because we cannot access all the data in the private mobile phone and use the data for training a large neural networks. So in this case, considering the federated learning seems to be unavoidable. So what is it exactly federated learning? Suppose we have 3 clients or 3 machines. There are mobile phones, laptop, and the workstation, the laptop workstation. So they have different minimize objectives F1, F2, F3. X is the parameter in each client. So in federated learning, we have a master or another large workstation. This workstation receive the outputs from each client. That means this workstation will receive F1, F2, F3 with parameter X. And this workstation will do the naive average over all the clients. After computing the average, then this workstation will send the averaged results to each client. This is the basic idea of federated learning. By the way, feel free to interrupt me if you have any questions anytime during my presentation. So now, from the mathematical perspective, in federated learning, we are trying to optimize the mentioned average over all the clients. N is a number of devices or machines or clients. You can call whatever you want. And this D is the dimension of the model parameter or feature. So the X is the model parameter. And Fi is the local objective, just previously mentioned, and is computed as the expectation of all the local data, Di, that is stored on device I. So Fi(x) equals to the expectation of Fi, given all the data, zeta belongs to data set Di. And we noticed the main difference of federated learning and the standard distributed training is that nowadays the data sets D1, D2 to Dn for each client can be arbitrarily heterogeneous. That means the distribution of Di and Dj when I and j are belonging to 1 to n can be significantly different. However, in traditional distributed training, it's impossible. And sorry, that is a sketch here. Could someone just erase it or? Okay, let me do that. Okay, so for distributed gradient descent, this is exactly what we did in the very beginning. So recording our optimization problem is the average over all clients Fi. So suppose we have 3 workers, F1, F2, and F3. Then we have a server. So for each worker, let me just focus on the worker 1. The worker 1 receives xt from the server, and it assigns this st as its local parameter x1, t. Then it runs one step or single step gradient descent. So they computed the x1 t plus 1. X1, the 1 here is the index of the worker number, and t plus 1 is the iteration time. So the very standard gradient descent contains the x1, t minus gamma. Gamma is the learning rates times the gradient of x1 given xit. Then for this xit plus 1, it will be sent to the server, and the server will do the aggregation of the 3 F1, F2, F3. Then after that, the server will broadcast the averaged or the aggregated results xt plus 1 to all the workers. And this is exactly what is distributed gradient descent. However, the training efficiency for distributed gradient descent, or the abbreviation DGD, is not efficient, and sometimes even not converge to the exact global minimum. Another different consideration is the distributed local gradient descent. What's the difference between the distributed local gradient descent with respect to DGD is that nowadays each worker performs K gradient descent step using its local function, and the results are averaged. In previously, we only consider the one-step gradient descent. The brief idea is almost the same and the setting is the same, but the only difference is here. So for DGD, after getting the x1 t plus 1, we will send it to the server. However, for distributed local gradient descent, we will continue updating the local parameter x1. So we get x1 t plus 2. Then after k iterations, we get x1 t plus capital K. Then we will send the final results to the server instead of the first result. Then we do this average, and then we send back to the server. So this is what exactly the distributed local gradient descent. However, even though this method has been started for more than a decade, however, this method is not is problematic and contains a lot of issues that I've listed here. The brief history of local training methods, or just like I mentioned, distributed local gradient descent, at least contains 5 generations. The first generation is what we call the heuristic. In that area, there is no theory for local training, and intuitively, there is no assumption as well. They only obtain empirical results to say that by local training, your methods will receive the reduced communication cost. However, we don't know anything why. The next generation is what we call homogeneous. Now we first have the theory. However, the assumptions are unrealistic. So for example, the bounded gradients or the bounded gradient diversity, which means we do not allow data heterogeneity among clients. This is exactly the standard distributed learning instead of the federated learning. Because in federated learning, we assume that all clients should be data heterogeneous. Besides, their communication complexity is sublinear, nor linear, but worse than the gradient descent. The next generation is sublinear. They have standard assumptions like the mu convexity and the L smoothness for each function fi. However, their rate is sublinear. Then later, it contains the linear communication complexity under standard assumption. However, their rate is also worse than gradient descent. Only recently, we have designed the accelerated local training methods, starting from the Ph.D. paper, which was accepted at ICML 2022. And this is linear, and the communication complexity is better than gradient descent. From our perspective, we further contributed it with a lot of new characteristics. This talk will discuss 2 of two papers that I contributed. The first one is PROSCIP VR, variance reduced PROSCIP. So for the 5th generation local training method, we call it accelerated because the following reason. The communication complexity of the 4th generation local training methods, such as the scaffold or fettling, is L over mu log 1 over epsilon. However, for the later version, the communication complexity is reduced to be the square L over mu. This is a very huge improvement over the whole local training community. Suppose that L over mu is 10,000. Then in this case, the square will be just 100, which means this rate is 100 times faster than the previous 4th generation. Or from a different perspective, if you assume the same iteration, then the communication complexity for the 5th generation local training method will be highly reduced. And then here goes our first paper, the variance reduced PROSCIP. Just like mentioned here, we further contribute to 5th generation local training methods by enhancing it with variance reduction. What is exactly variance reduction? This is a technique used here. Let me show it to you. So for a non-variance reduced methods, if we use the unbiased gradient estimator instead of the full gradients, just like the gradient descent, the SGD-based methods will only converge to a neighbor, as we can see from this figure. So just let me show it some door. Okay, so we can see here. Let's focus on this method. This method will converge to a neighbor. So we can see here, this neighbor. So suppose the optimal F star is something like this. And the neighbor shows you will only converge, you will only get the results to be something like this. F star minus epsilon and F star plus epsilon. And this epsilon could be a bit huge. So here it seems to be 10 minus 5. So this is not variance reduced. However, we want to have a version that is variance reduced, is what we call the PROSCIP VR. We can see that this is not exactly to the F star here due to the computation system error. I mean, this part is due to the system error because this is lowest accuracy that we can achieve by using some techniques. So, but we can see here, this is almost converges linearly, and this is as well. Going back to the previous figure, let me show it. So this is what we propose the PROSCIP VR. This is the brief algorithm. Maybe I just skip it a little bit. We can go back if anyone is interested. But yeah, so we can see that our method converges linearly, and this convergence rate is guaranteed with different tau. Tau is a number of batches. So this is similar to this, because nowadays for distributed local gradient descents, we do not compute the exact gradients with full batch, the gradients of F1, X1, comma T. Here we consider the stochastic estimation. So this is the batch size behind the stochastic estimation. And later, we are the first to consider the total cost instead of communication cost, because for local training methods, we will always run, for example, k local iterations. In the previous literature, we all assume that the communication cost among clients to the server to be expensive. However, these k iterations can also be expensive if your device, the capacity of your device is highly limited, or you have a lot of local data to compute. In this case, we try to consider both the communication cost and the computation cost as well. We designed the total cost to be the communication cost plus the delta times computation cost. This is the formulation. And we consider different scenarios with kappa. Kappa is defined as L or mu, and the different batch sizes, tau from 16 to 64. More detailed results can be found in our original paper, but here we can see if let me just focus on one figure. So supposed to be the leftmost one, and the x-axis is the computation cost per sample delta, and the y-axis is the total cost ratio of proskip over our proposed proskip VR. Yes, I saw a question from the QA box. Sorry, I just received it. Oh, the question is, distributed gradient descent in machine learning can be applied for classification? If yes, please provide more detailed example. Okay, so I will illustrate it after I finish the total cost illustration. So basically, we can see when the computation cost per sample to be large, but not that large, our communication cost will be significantly reduced compared with proskip because the Y ratio is getting large. Let me give you a detailed example. So to show here. So suppose now the computation cost per sample, the delta to be 10 minus 2. Then we will get almost 12. 12 is the number of communication costs of proskip, the first paper, and over our paper, proskip VR. So we can see the ratio is 12. This is a significantly improvement when the communication cost is getting large. However, we also notice that in federated learning, the computation cost is not that severe compared with communication cost. So we do not fully identify all the results to make the delta to be very huge, like 10 or 11, or even 100, something like that. So here, like I mentioned, proskip VR outperforms all other methods significantly due to its communication accelerated properties. So going back to the previous question, distributed gradient descent, yes, exactly, can be applied for classification. This is what exactly we can do here. But let me show you some intuitive example. So I'm not quite sure if you are familiar with MList, the very standard image classification data sets. So here, FEMList is the federated version of MList. This is for image classification. The brief setting is as follows. Let me show it. The brief setting is as follows. You also have, suppose you have 3 clients. Each client has a model and is F(I)(X) as well. This is F3(X). And then you do this aggregation. However, suppose in FEM list, you have 60K samples. Now you have 3 clients, so each client will receive only 20K samples. You will use this 20K sample to train this FIX. Then after training it well, you will aggregate all of them to the server, getting a larger model. Then if we are running the ERM as the objective, after training it well, you will use the global model with each parameter to do image classification. So suppose this is the ResNet 18. You will use this trained model to do further classification on FEM list. Has this answered your question or any other questions? Yeah, feel free to let me know if you have further. Okay. Okay, let me go back. Okay. So this is the first paper I want to introduce, the variance reduced proskip, which was accepted to NeurIPS 2022. And later I will introduce one of our recent paper, just released several days ago. Do you have any questions about the first paper or some conceptual questions about federated learning? Okay, I received another question. So the first question says, in federated learning, is it lead an assumption of the balanced data sets for each worker? For example, when the device is also used for collecting data sets, it's likely that one device may collect all data sets, and updating the model's parameter could encounter bias in learning towards the device has more data sets. How federated learning can handle this? Yeah, this is exactly a very good question. In federated learning, from the theoretical side, we do not assume any balanced data sets distribution for each worker. That means, like the previous example just I show FEM list, I assume that each client has 20K samples by uniform distribution. This is for the convenience of experiments. However, we also have done some work like doing sampling with the beta distribution, which is the imbalanced one. So beta distribution is also widely used in verifying it. Also, in recent literature, they also consider that each client has very severe different capacity to compute. That means for client 1, it may have 50K samples, but for client 2, it will have 5K samples. This has been studied in literature, and this is for the experimental results. From the theory perspective, we do not assume they are balanced, and our theory can work well for both balanced or imbalanced data sets. So we do not care about this. Another question is that the different qualities of the visual sensors in each device, is it will also affect the learning, or does the data set actually stay at a server first, then the I'm not quite sure if I understand your point well. Another question is about the different qualities of the visual sensor in each device. Do you mean that different clients have different capacity to compute and they have different processing time, even though you give the same number of data sets, data samples? If I understand correctly, and let me answer it as follows. So for this ProSkip and VR ProSkip, we do not assume that some clients will send the gradient later. So we assume they will send the feedback in parallel. However, in some other literature, also some work that was conducted in our group, we just like the paper GraphSkip, it contains the setting that each client can send its gradient back to the server anytime if it wants. So this is not a big problem in the real scenario. And from the theoretical side, theoretical perspective, there are also a lot of works. Okay. Another question is, can this federated learning possible applied continually over time? Yeah, this is another good question. I would suggest you to have a look at recent paper by typing federated continual learning. This has been studied in several papers, and but this is beyond the scope of today's discussion. If you are interested, you may have a look. I hope this answered your question. Feel free to let me know if you still have any concerns. Okay, so now I would like to introduce another paper, the recent one, Explicit Personalization and Local Training, Provable Double Acceleration. So the brief idea is that we further contribute to 5th generation local training methods by enhancing it with explicit personalization, leading to provable double acceleration. What exactly, why we need to consider the personalization? Because suppose you have a lot of mobile phones or devices, everyone is unique. You do want to have a personalized model that can be applied based on your real case, but preserving your privacy. So this is the main focus. We found that by designing the explicit personalization, combining with local training, we show provable double acceleration. And in practice, it works really well. Let me show it with more details to you. So instead of previous ERM, now we consider the explicit personalization objective. Recall in the previous ERM, or the average over all the clients, we will do FI with respect to the global parameter X. But now for explicit personalization, we consider the mixture of the local and the global one. As we can see here, this alpha I is a personalization factor, ranging from 0 to 1. And the XI star is the local optimal model. So we assume that for each client, it contains the linear combination of the global model and the local model by a personalization factor alpha I. This is interesting, and it can show very surprising performance in real practice. So let me give you some intuition on what exactly happened by designing this alpha I. So suppose if alpha I to be 0, that means this, let me show it. If alpha I is 0, that means this will left out. We only have this, and this is also 0 and left out. We only have this. That means we do not do any communication at all. Each client will only compute the local optimal model without communicating with the server. On the contrary, if this alpha is getting large and to be 1, that means we will only have this. This will left out. That means there is no local optimal personalization. Sorry, low local personalization, and we do not consider local optimal model. So in this case, this is exactly the average over all the clients, because nowadays this is just Fix. So by some good personalization, which means by setting the alpha I to be a good value, the personalization factor alpha I to be a good value, we can have some degree of personalization, but also consider some communication. This is exactly what we want in practice. And then this is what we call the explicit personalization objective. And then we propose a bit complicated algorithm, Scarflix, for solving this problem. So again, I will go back to it if someone is interested, because this method is a bit complicated. So and mathematical heavy in some sense. So I will go back to it if it needed. Then we want to show in practice the double acceleration caused by local training and explicit personalization. Let me just focus on the first figure. Okay. So if we just focus on these two lines. So as we can see, every dashed line like this, every dashed line is running gradient descents, and every solid line is running our proposed Scarflix. As we can see, the only difference between these two is whether you run local training gradient descents, and both of them are optimizing the explicit personalization objective, like here. They're all running this explicit personalization objective instead of the average. So as we can see, by running our methods, Scarflix, our convergence rate is better than gradient descents. And then if we think from a different perspective, only consider the dashed lines or the solid lines. Suppose now we consider the solid lines, which was conducted by running Scarflix, these blue, orange, and green, red, and purple. So we can see at the very starting point, the distance of the current value to the optimal F star is getting smaller and smaller. This is expected. Let me give you a more detailed introduction. So the blue line is considered the case with alpha equals to 1. That means, let me go back to see what exactly happened with alpha equals to 1. If alpha goes back to 1, like I previously mentioned, we are just running Fix, the intuitive, the very naive average over all the clients. There is no personalization at all. With more personalization from here, with more sorry. If with more personalization, that means we start from this line. Our initial distance over the global optimal F star will be smaller and smaller. So we have shown the double acceleration in practice on a lot of large-scale data sets. And later, yeah, this figure is very typical to show what exactly our finding is and may conclude the whole contribution of our paper. Later, we consider some large-scale experiments. For example, the image classification on federated EM list datasets and the Shakespeare datasets for next word prediction. This is from the NLP domain, natural language processing domain. And we can see here, this we want to check with limited communication runs, what will be the testing accuracy for different methods. The green lines are our proposed snowflakes from 2 data sets. As we can see, compared with the baseline models, baseline algorithms, fed average, which is a very standard and popular in federated learning. And the Flix, another paper, also consider the personalization. Our methods is working really better than theirs, especially for a bit difficult next word classification. So, next word prediction instead of the image classification. So, I mean, the right figure. The gap between the green line to the orange line or the brown line are getting huge and huge. This verifies our methods can converge much faster than their method, and even our convergent results will be better as well. Here I show some key application studies. The first one is the evaluation is the influence of different personalization factor alpha. Alpha is varying from 0.1 to 0.9. We found that on average, by setting alpha to be 0.3 works better on the FEM list data sets. So that means here, without a variance, this one will get the result like this, but all the other methods will only show something like this. Our method is better by setting alpha to be 0.3. We also noticed in the supplementary for each different data sets, the personalization factor alpha can be different. The second figure is the effect of different number of clients participating to communication. Because in practice, for example, in FEM list, we have 3,400 clients. We cannot use all the clients to compute, to do the average for each round. So we need to select a particular number of clients to participate in communication. So here is the ablation with different number of clients. We have found that by setting the number of clients Tahu to be a bit large, like 10 or 20, the testing accuracy could be higher. But we also can see here, the difference is not that severe. And the last figure is the comparison of different values of the communication probability P. P is getting from here, from the algorithm itself. P is the probability of communication. Let me show it. Yeah, theta T. Flip a coin. Yeah, like here. Flip a coin. If theta t equals to 1 with probability p 0 otherwise. So here it is. And we found that with smaller p, the testing accuracy could be better with limited communication runs. This is also expected. The detailed illustration has been provided in our paper. Interesting reader could have a deeper look at it. And this is the whole thing I would like to share today. Do you have any questions? Yes? Oh, let me see it. Okay. I saw a question from the panel. How this personalization factor for each worker is chosen in the first place? How does it mean that the factor is close to 1 on FI and alpha close to 0? How do you decide it? Yeah, this is a good question. So briefly, we assume this personalization factor alpha to be a hyperparameter. That means for this paper, maybe this could be an interesting direction for further exploration. What can be the optimal personalization factor for each data set? But our experiment shows for each data set, they are different. I mean, the optimal alpha are different for each data set. So this could be interesting in future work. In our case, we always try different alpha chosen from 0.1 to 0.9 or some other different scales. But one interesting thing is, no matter what we choose the alpha is, for example, alpha equals to 1 or alpha equals to 0.1 or 0.9, we can also see the improvements over the results without explicit personalization. And then let me answer you another question to see what exactly will be happening with different alpha selection. So remember that in the previous literature, we consider the following optimization problem. This is exactly like this, right? So this is exactly the average over all the Fi with the global parameter X. But now here, we consider a different case, consider the explicit personalization. So if alpha I equals to 1, if alpha I, this alpha I is equals to 1, that means 1 minus 1 will be 0. There is no something like this. That also means we are exactly computing Fix. This is exactly the previous average results. So if alpha I is getting smaller and smaller, which means more personalization, the extreme case is alpha I to 0. That means we do not consider any global involvement because we do not consider the global X for each client. So for each client, it just runs Fi Xi star, which means no communication because it just compute the outputs from the Xi star and then do the average. So we assume that to some extent, by choosing alpha I elegantly, we can have some personalization and also have some communication acceleration, which was verified in this figure, in these figures. Okay, I hope this answered the question. And another question is K iteration also means generation? Let me clarify this. What is K here is like this. So we call generation is talking about the different local training methods. We categorize them to be 5th generations. The presented two papers, ProSkip VR and the later Scarflix, are all in the 5th generation, which is accelerated generation. And to the best of my knowledge, the Scarflix has the best convergence communication complexity in this accelerated area. What we mean K iteration is the number of local training, like mentioned here. How many iterations you did after before sending it to the server. So in this case, we send this XIT plus capital K to the server. This K means we do K local iterations. Is it clear? Yeah. Feel free to let me know if you have any further questions.
Okay. Any other question for from participant? You can use the we will open the raise hand feature. You can use this raise hand if you want to ask. You can open mic. We will choose before that. Okay. Okay, dear ladies and gentlemen, you can choose the we will choose. Please open the raise hand if you want to ask with the feature raise hand. Okay, anyone? Okay, Mr. Andy, go on.
Okay, thank you very much for your very interesting research about this federated learning. There are some questions from me. First, like how about the noise when there is a noise occurred during the communication in the local device to the server workstation? I mean, yeah, maybe that's first. And the second is like let me choose. I have several questions in here. How many K in the local gradient descent needed for, like, let's say a time series data, like, or I don't know what kind of applications you run on the device.
Okay.
And like in this communication cost and computation cost. And what do you mean by the cost? Is it like the flops or the parameters of the gradient descent or something like that?
Okay, yeah, they're all good questions. Let me answer one by one. So firstly, let me answer your third question. What exactly we say communication cost and computation cost? Because this is a very good figure to show what's happening here. So what we call the communication cost is the green line. Oh, sorry, is the yellow lines. So when we send this XIT plus K to the server, this is one communication. We assume for every communication, the cost will be 1 unit. This is exactly 1. And what we say the computation cost is this. This is running gradient descent. For each running, the cost will be n delta. Delta is the ratio of your computation cost over the communication cost units 1. So in this case, n is the number of data. Because you run gradient descent, then you will have n times delta computation. If you run this k step, this will be multiplied by capital K. This is exactly what the computation cost and how it's computed and the communication cost. Is it clear?
Okay, I understand till that part. So you don't calculate the parameters or like the floating operations inside the local server or
Yes.
worker.
Yeah, because ideally we care, because for different methods, the number of parameters, what I mean here is the dimension of X is the same. So for example, just belongs to alpha D. So we do not consider something like this, but the communication cost and computation cost can be also representative to show.
Right. The unit can show this as the cost. Okay, thank you so much.
Yeah, the second question you mentioned is that how you choose the capital K in your case. This is a very good question, and for different papers, we have different theoretical steps. For example, in our first paper, ProSkip VR, we choose the capital K to be like this. This is kappa. Sorry, avoiding misconfusion. Let me just show you this. L over mu. L is the L smooth term, and mu is the strongly convexity for each function. So kappa is chosen. Sorry, I missed some. It should be this, and then we will get. Sorry, let me show you, because previously we used kappa, but now we use this. So the K, the iteration K is to be the square of L over mu. This is for variance reduced ProSkip. In the second paper, what I introduced, the flakes, scar flakes, we consider K prime to be something like this, L min, because for each client, we may have the different L min. In the ProSkip, the L is for the F, the global L smooth for F. But here we consider the personalization, so we specialize on Fi. Kappa prime to be this term, the mu max. Yes. Yes. Is this answer your second question?
I see. Okay. So it also depends on the length of the data that we will. Yeah. Okay. I understand till that part. Okay.
Yes.
Thank you so much.
Yes. Can you repeat it a little bit about
the first one is how about the noise? Like, of course, there is a noise when you send the data from the, let's say, worker 1 or worker 2 to the server. Like, let's say the calculation goes wrong, or time consumption is different from one worker to another worker, and the server will do this calculation together, like collecting them. So there are two computation running together.
Yeah, I understand your point. So you mean that if we consider the stochastic estimation of each client and do the average over all of them, we may have some noise or some what we call some bias towards the real global optimal, right?
Right. Yeah, global optimal.
Yeah. So in this case, this is exactly what has been shown in the literature. So for the baseline method, for example, stochastic ProSkip as local SVRG, we will see this noise violates the final convergence. That means it will only converge to a neighbor. So to some neighbor, the given solution will not be exactly the optimal. Is stuck at that place. So we need to consider some variance-reduced mechanisms, just like the one presented here, proskip variance-reduced VR. This is one thing. The second thing is we consider reducing the noise by constructing a new controlling vector. So if you just want run the distributed gradient descent, you don't need this, right? You don't need to have this y0 here, or reflecting on this HT as well, the gradient shift. You don't need to have something like this. You just need to get the gradient estimator, GT, then you compute this, and you just update it with GT, right? Is it? Do you understand?
Okay.
So,
okay. For
yeah.
this, I think I need to read the paper.
I see. So
thank you so much.
Yeah. So the brief idea. Let me talk a bit high level. We introduce a new gradient shift controlling parameter H0 or the HT. It will be changing by iterations. We introduce another controlling parameter to reduce the noise caused by different clients or by different stochastic estimation. Yeah.
Right. Then you previously said that you have a kind of noise reductions algorithm as well inside this.
Yes.
And yes. Which means that probably will be another research, of course.
Yes.
And will it be possible to apply like kind of filtering, noise filtering, like a Kalman filter, particle filter, things like that in here?
Maybe it's possible, but from our perspective, it's a bit not quite elegant in this case, because if you run the Kalman filter, something like this, you do not have a good guidance when the iteration is going on. What I mean here is that nowadays we introduce the gradients controlling vector HI, which can be learned and can be converged. This is theoretically provable. If we use the Kalman filter, maybe you can find a good place to insert it, but I'm afraid it will be a bit difficult because we do not have any assumption on what exactly the noise is. For example, in computer vision, the typical noise is designed to be the Gaussian from the Gaussian distribution, but here it can be any distribution or even from the system level noise. What I mean system level is that the architecture of each client can also be different. So I'm not quite sure if Kalman filter can handle something like this, but it also could be interesting to do further research. Yes.
All right. Thank you so much. This is a very great discussion. I hope you enjoy your PhD.
Yes, thank you so much.
Thank you. Maybe another question, the last one before we are finish this webinar. Maybe the last one from the participant. If you have question, you can use the raise hand feature, or you can drop in meeting chat. Masya Allah, this is the presentation that really comprehensive and detailed. We are thank you for the Mr. Kai before we finish, maybe any one question, the last one from the another participant for the other question participant or the ladies and gentlemen. Okay, you can use the raise hand, or you can use or open mic before we finish this webinar. Okay. Okay, I think no question. So before we are finished, please give the closing statement for this webinar today, Brother Kai. Hello, brother.
Yeah. Thank you.
Thank you. Maybe you want to give us the closing statement before we are finished today. Hello.
Yeah.
I mean, please give the closing statement to us before we are going to finish this webinar.
I see. Okay, so you mean for me?
Yes,
Sorry.
I mean you.
Okay. So today, the introduced accelerated local training methods in federated learning is a very, I need to say, a very important direction and has been widely studied nowadays. There are a lot of potential work towards this area. So for example, like the previous suggested, how you can have the optimal personalization in local training, how you can prove it works really well. Another thing is for local training, nowadays from the theoretical side, we do not consider much complicated cases such as the non-convex setting, which is very standard in training the neural networks. So this could also be interesting for that. And from the practical perspective, whether this local training can be applied to the very high level, very severe data heterogeneous settings, this could also be interesting, and how to prove it when you have the system level error, something like that. This is not explored yet, but could also be very essential in making local training better in federated learning. So I hope this presentation today helped you learn a little bit about federated learning and what's going on here. And feel free to let me know if you have any questions, no matter in these papers or in some future thoughts on how to do it. I'm more focusing on the theoretical perspective, but I really like make it runnable in the real world. Thank you.
Okay, Masya Allah, thank you. Really, Chanda, Hen Singkoni. Really, we are appreciate because you are coming to our webinar. The last one, it is possible we are joined to your research lab. Maybe KAUST will be open. The open position for the researcher like Ph.D researcher, or maybe postdoc. Maybe we can join to one lab. VCC in I think in VCC. No, you are in VCC or in different lab, brother.
I'm also offline in VCC, but I'm mainly offline in AI initiative now. Yeah. Yeah.
Okay. So maybe participant in this webinar, you are interested to join KAUST or as a student or researcher or postdoctoral, you can apply. But no is the submission will be closed because the time is not enough. I think maybe next year or next semester you can apply to participant if you want interest. Okay, thank you so much. Really 很辛苦你来这个活动这个的很辛苦，我们的谢谢非常感谢。Really, thank you so much and appreciate to present our and coming this webinar. And we will thank you so much also to attendants or participant to join this webinar. And don't forget to join us in the next session or the event. Maybe we will also invite another researcher and also professor in abroad and overseas to share their research and also project. Thank you so much, Mr. Kai, to coming and also participant. I'm Ripto Wibowo from the BelajarBerbagi. If any wrong or any mistake from this event today, we will do. Thank you. Sorry, we will ask. We will sorry, and we want to again thank you so much for this join this event for Mr. Kai and all of participants. And see you in the next event. Assalamualaikum warahmatullahi wabarakatuh.